Welcome everyone. This is our 9th RPF Computing Education and Research Seminar of 2025. I'm Jane Waite and I'll be chairing the session today. And again this year we're focusing on teaching about AI and data science and exploring research that examines what students should learn and how we might teach it. And today I'm very excited because I do think that Viktoriya's work is going to influence both what we teach and how we teach in really profound ways. So today I am so excited that we're looking forward to hearing from Viktoriya, who's going to lead a seminar on data-related concepts and practices for AI education in K-12. I am so excited and so pleased to welcome our speaker, Viktoriya Olari from the Free University of Berlin. I met Viktoriya a while ago on conference and we just had the best time, and I've kept in touch with her since, and she is a researcher to watch. She's doing the most amazing research. She's a PhD student in the Computing Education and Research Group at the Free University of Berlin with Ralph. Her work focuses on AI and data education, and she's contributed to many initiatives aimed at helping teachers and students to develop a deeper understanding of these topics. She also serves as a member of an AI literacy expert group for the Council of Europe, and she is an advisory board for the Data Civic Lab in Germany. And today she's going to share her research on data-related concepts and practices for AI education in K-12. And she's going to share with us a model that I really do think everyone will soon know, which is kind of her data-related practices and concepts lists. But most importantly, she's going to share with us something that has not actually been shared anywhere else before yet. She's presenting at a conference very soon on this, and it's how her case studies how they panned out when she was in schools. And this is the pedagogy bit, and I'm very excited that she's going to share that with us. So without that, with all that, here over to Viktoriya, and let's listen to her wonderful research.
I'm very, very happy to have you all here and share the results of the recent work that we've conducted in our research group. Well, actually, it's still an ongoing work. We've been working on the research for probably the last 4 years, I guess. And so there is a lot, there are many things that I'm going to share with you. So the talk is kind of very content heavy. So please stay tuned. So in the first, the talk is actually structured in 2 blocks. So in the first block, I'm going to talk about what should we teach our students about data when we teach them about AI systems, so the key data-related concepts and practices. And this is the result of the theoretical research that we conducted several years ago. And the second block, I'll introduce you to a method that we developed in collaboration with teachers, domain experts, and students to teach about this data-related concepts and practices under real school conditions. The method is called the data case study. And this is, the result of the design-based research project that we conducted over the past 2 years. And I mainly will speak about different forms of the data case study method, so how you can teach it in the school, and also mainly about the challenges that we encountered in the school when adopting this method. Because some of you might not be directly from the AI education area, to help you get settled, I give a brief introduction of why teaching about data in the context of AI is relevant in school education, and I will speak particularly about Germany, so my home country. And at the end, I'll summarize the talk and talk about the possible implications of our findings for the future research and education. All right, so let's dive in. So I'm greeting you today from Germany, and right in the heart of Europe. And it's a beautiful autumn here. Yesterday I took this photo on the campus on the university. As Jane said, I'm located in Berlin, in the Free University of Berlin. And on this map here on the left, you can see Germany in autumn colors. So these colors, they aren't just for decoration. They actually represent the current state of computer science education in Germany. So Germany is a federal state and education is a state matter. So there are 16 states in Germany, and each of the 16 states decide whether to teach computer science, how much computer science to teach, and which topics to cover. So now, as you can see on the map, many states, all marked in the green color, have compulsory computer science education. So they mandate their students, starting from the grade 5, to learn computer science for at least 1 hour a week. And this leads in some states, such as Mecklenburg-Vorpommern, to offer over 200 hours of computer science education per year from the grade 5 onwards. Now, what we are now observing in Germany is that AI topics are entering the formal education for computer science. And this is really happening, on the unprecedented speed. So, for example, in North Rhine-Westphalia, the state curriculum for the 5th graders, so for computer science, included learning about machine learning with decision trees and neural networks. Now, while these new additions to the curriculum, they are really timely and they're really important, before actually introducing a new topic into teaching, we really need to think, what are these fundamental concepts about AI that we want our students to know and to understand? And so in computer science education, there is actually generally a strong consensus that teaching should focus on these key concepts of the subject matter rather than on the fleeting technological development. And, for the broad area of computer science, there are some well-founded collections of the key concepts. So, for instance, well known in Germany, but I think also worldwide, are the fundamental ideas of computer science proposed by Andreas Schwill in 1994. But also great principles of computing proposed by Peter Denning in 2003. Now, the thing is, for the field of AI, the conceptualization is still ongoing. So we are still in the process. And it is very challenging because the field is constantly evolving. So several catalogs of competencies and ideas have been proposed. So for instance, well known are the big ideas on AI from the Dave Turetsky and his group. However, from the prior research that we conducted several years ago, we learned that some major subject areas, they remain very much underrepresented in the AI education so far. And the most striking area at the time was actually the data domain. So we found that competency frameworks, they critically underestimate the fundamental role of data in the whole data-driven system development. And so, for instance, here you can see on the left, we compared different frameworks, and you see, for instance, the data cleaning hasn't been addressed in none of the frameworks that we looked at. Now, modern AI systems are data-driven. And so if we want our students to understand, evaluate, and use responsibly, and maybe even design such systems, they must understand the data. So, for example, if we want our students to be able to evaluate such systems, they must be able to operate with a range of concepts, right? Concepts such as test and training data, data quality, data bias. But they also need to develop an understanding of data practices. So how the data was collected, how was it cleaned, how was it preprocessed, how was it modeled and implemented. And so following this tradition, of thinking and organizing teaching in K-12 around central concepts and practices, we posed the following research question. So what are these key data-related concepts and practices in the context of AI that our school students really need to know? In order to answer this research question and identify the data-related concepts and practices, we built the research around 4 steps. And I'll talk take you through every single step, but I will speak mostly about this conceptualization step because I really think that you need to understand what the concept is and what the practice is in order to understand our models and the collection of the key data related concepts. So in the very first step, we needed to conceptualize what are we actually looking for, well, what are the concepts in, how to define a data-related concept and the data-related practice? Well, in sciences, when we look in sciences, where other sciences, they also work with concepts. The concept they are described as a systematic mental representations of the real world. And they might be observable, so they might describe an observable entity, for instance, something like a mountain. They might describe an unobservable entity, something like an atom or maybe an abstract entity. And they also might relate to a process, something like the photosynthesis. And so following this understanding of concepts in sciences, we defined a data-related concept as a term that is used to describe a specific process, an observable or unobservable entity related to data in one of the stages of the data-driven life cycle. And you see this data-driven life cycle on the right. It consists of 8 stages. So typically you begin with the understanding of the data. So what kind of data do I need? Understanding the task. Then you're collecting the data. You're trying to understand the data, preparing the data, implementing the solution, so using the data to create a model. Then you are evaluating the performance of your model with the testing data, for instance. Then you are deploying the system, and then at the end of the life cycle, sharing, deleting, and archiving data. So to give you just an intuition how these concepts might look like at different stages, I have 3 examples. So let's say, what could be an example for an observable entity? So this could be something like the training data. So here you see the training data that I created to build a classification system for healthy and unhealthy food. So you can literally open the folder where the images are stored and inspect its content. So I can observe it. An example of an unobservable, an abstract entity could be something like data modality. So while, it refers to the form of how data represents the information. So while you can directly, for instance, observe the image or the text, the concept of the data modality itself, it's not something that you can observe. So it's an abstraction that we use to categorize different types of data according to its representation form. And the example for the process could be something like the data augmentation. So this is a process of enriching or expanding a data set by creating modified versions of the existing data. So for instance, for an image classification context, the data augmentation might involve flipping, rotating of images to increase the diversity of the training data and improve the robustness of the final model. All right, so what is a practice now? Well, in sciences, practices basically are actions, something that the scientists do, something that they perform to build up knowledge and theory. So, for instance, the scientists, they plan the investigations, they carry out the investigations, scientists, they develop the models or they use the different models. So this notion of the action that is performed was also something that we took as a foundation for our definition. So we said, well, the data-related practice is actually it is an action that is performed on data or with data in mind on one of the stages of the data-driven life cycle. And here is an example, for instance, on the implement solution space. It could be something like splitting a data set. So splitting a data set is an action that I'm performing on my data set. Or training a model with a training data. It's also a practice that I'm performing with my data when I'm building a model. All right. So far, data-related concept, data-related practice. Now, in the second step, because we wanted to find the data-related concepts and practices, so how can we come up with this initial list of key candidate concepts? The thing is, because the AI field is developing really fast, you really need to deep dive into the domain in order to assess if a particular concept is really fundamental. Can you observe it in a time, in a time manner like several years ago, or is it a new one, or is it already here for several decades? So you really need to get deep into the domain. And so in the second step, we selected some theoretical literature about the AI system development and conducted an in-depth analysis of it on the data-related concepts and practices. And while engaging with the sources, we manually extracted the initial list of data concepts and practices along with their descriptions. And I think we ended up in a document of 111 pages or so, containing our candidates for the key data-related concepts and practices. Now, in the third step, in order not to develop the whole collection in isolation of the school practice, we also went through several competency frameworks on AI education to get a sense of representativeness of our collections and to understand if we don't miss anything is important. And lastly, we corroborated our results with the domain experts, so mainly the data scientists who work in the data science field, but also with the teachers on the usefulness of the collection of concepts and practices for their teaching. And I have to admit that after this step, we really drastically reduced our collection of the concepts and practices. So the final collection that I'm going to present on concepts and on practices is really a reduced version of this initial one that is validated by professionals and also aligned with the school education. So let me give you an overview. So the model of practices, it contains practices that are performed on data during one of these 8 stages of the process of the data-driven life cycle, from understanding the tasks that I already mentioned, collecting the data, to sharing, deleting, and archiving the data. You see, this process looks kind of sequential, but in the reality, it's not. So it's very iterative in the real world practice. And in total, we identified 28 key data-related practices. To make, this collection usable in the school education, we also proposed 69 examples of sub-practices for use in computer science education. So let me give you an example. I already gave some examples on the practices, but here's maybe another one. So if you look into the one step, for instance, let's say prepare the data, you will see this, the key data related practices, they are marked in purple. So they are the key data related practices. And then there are some examples of the sub practices. So here, for instance, for the preparation of the data step, the important practices are clean the data, pre-process the data. Pre-processing of the data, it always depends on the data modality that one has. If I work with the textual data, for instance, I would need to lemmatize, tokenize, like do the preparation of the textual data. If I have image data, my pre-processing step would look different. Then another key data related practice is data labeling. So label the data, augment the data that I introduced earlier. The collection of the data concepts is also similarly organized around these 8 stages of the data-driven life cycle. And the concepts, they are grouped in 12 sections, let's say. So for instance, here on just an example of 2 sections that are relevant, 2 sections of concepts that are relevant in this understand the data stage. The concepts for the data exploration and the concepts for the data quality control. So for instance, what is important to know in the data exploration? Well, you probably need to understand what the data set composition is about, and these are statistical concepts, something like, okay, what is the data distribution? What is the correlation? What is the variance? So you need to understand some statistical concepts. And in the data quality control, there are different types of biases that might occur in the data. So for instance, something like the representation bias or measurement bias and so on. So because we are now in the community of AI educators and people who are interested in maybe how to apply this model, what I decided to do in the next slides is to show you how can the teacher use the collection of concepts and practices to specify what to teach. So how could this process practically happen? Now, imagine that a teacher wants their students to master the following competency. Describe how to design an AI system. Now, this is actually a competency that I borrowed from the recent OECD framework on AI literacy. So as you see, it's actually a very broad competency that touches on many stages of the data-driven life cycle. And so when planning the lesson, the teacher would start, with this very broad competency, but then go backwards, and here is where the teacher can use our collection as a guide for the orientation. So the teachers, they might ask themselves, well, what terms should my students be able to operate with? And AI systems can handle different kind of tasks. It could be classification, it could be clustering, it could be recommendations. So what kind of data-related database task should they be able to speak about? Because in the classroom you cannot cover all, so you have to decide what to select. And so after thinking through the process, the teacher might end up with maybe not more than 8 concepts that he or she is going to cover in the classroom. So for instance, something like classification, the sample size, label, feature and target, feature selection, training and test data, adversarial data. Now, because the competency says describing how to design an AI system, designing means that the students also need to have some understanding of the practices. And so the teacher can decide which of these 28 practices to cover within the time that the teacher has. So for instance, it could be something like the students, they need to be able to describe that in order to create an AI system, a classification system, let's say, one needs to create a data set, one needs to verify the data quality, label the data, perform some feature selection, and then use the training data to train the model and maybe, test the system, and then maybe with some adversarial data on its robustness. So at the end of the process after going through the planning process, the teacher might end up with the following specification of the competency, describe how to design an AI system. The students should be able to operate with the following vocabulary, and so operating means verbalizing and also understanding the vocabulary. And the students should demonstrate some understanding of the following practices that belongs to design of the AI system. All right, so I think this is one possible way of using the collection and the process model to specify what to teach an AI education. And if you're interested, we published 2 papers on the data concepts and practices. So on the left is a journal article where we describe how we derived the concepts, and we also describe the concepts in detail. And on the right, it's a conference proceeding on the data practices, where you can also read about different kinds of practices. I think the key takeaway is from this part of talk is that, both the collection of concepts and the process model, they are kind of linked, and it is really useful to use them together. The collection of concepts you can definitely use as a foundation for the common language that you want to establish when you are teaching about the data-driven systems. And the process model can guide you to specify the detailed competencies that you are going to cover in your classroom. All right, so far, we looked at what to teach, so the key data-related concepts and practices. Now that we know what is essential to teach, the question arises, how can we actually support computer science teachers in addressing and teaching these new data-related concepts and practices, new to computer science education probably, in the classroom? So if we look at the areas where teaching about data in context of AI naturally occurs, and this is, academic context on AI and data science education, we find that a very established teaching approach is the case study, and I called it data case study. So university students, they learn essential data concepts and practices in lectures, but to really understand, to truly understand these concepts and practices, they complete labs or case studies, which I call data cases. So the goal of a data case is to guide the students through the steps of the data-driven project using a specific data case. And here on the right, you see an example. So this could be a starting question. So how will particulate matter pollution develop in Berlin in the next 10 years? And then I might use the data set that is publicly available on the air pollution in Berlin and show the students step by step how to conduct the data set exploration, how to go through all the practices through the whole data-driven life cycle to answer this question. Now, because each data case works with the real data and the questions from the domain, and it guides students towards independent exploration from a learning theory perspective, the data case study is rooted in the tradition of situational constructivist and active learning. And we know from the research in academic context that learning with the data case study has positive effects on the interest, motivation of the students and their engagement, and as well as on their increase in knowledge and skills. And so the question is, well, why not to, enrich computer science lessons on the data case study? Now, the problem is, school is very different from the university. So compared to the data science students, school students, they lack the basic programming skills to work on the data cases. They also lack time to familiarize themselves with the context of the domain where the data comes from. But also similarly, the teachers, they don't have the capacity to prepare the data cases in the same way as the university lecturers. So a transfer seemed really like, anything but easy. And so we decided to ask two research questions. So the first is, what challenges need to be addressed in order to effectively use the data case study as a teaching and learning method in schools? And the second one, how must we adopt the data case study in order to overcome these challenges that we identified to meet the objectives of computer science education on AI? All right. So in order to adopt the data case study, we needed an extensive expertise from various perspectives. So from computer science education to systematically evaluate the adoption process, from the school practice, but also from the domain from which the data for a data case comes. And so we therefore formed a team of experts consisting of two teachers, one computer science, one mathematics teacher, from the domain expert in the area of data with, I think, more than 35 years of experiences of working with data, and with the two computer science education researchers. The research process followed the design-based research approach, and it consisted basically of four phases. So in the first phase, we had to determine what are we going to teach. So what our students should learn about the data concepts and practices. And here we based, the content to teach on our prior work on data concepts and practices, and selected those concepts and practices that are typically taught with the data cases in the academic education. In the second phase, we in the team developed the actual data cases for teaching. And I have to say, we drew some inspiration from the academic data cases, but we really developed them from scratch. And while developing them, we tried to implement what we knew about the school-specific challenges. So, for example, because we knew that the students have heterogeneous programming skills, we replaced the text-based programming with a flow-based environment, Orange 3, where the students can build, work visually with the data practices. So they work with the widgets representing different data practices and build individual, like every student builds a data flow. All right, so this was the second phase. In the third phase, the teachers, they taught with data cases in the school. And we as expert group, like we from the expert group, we observed the lessons. And we also systematically collected the data on the challenges the teachers and the students experience. So for instance, after each lesson, we conducted an interview with a teacher and asked, well, what difficulties do you think the students experienced with the data case? How did they overcome them? But we also collected artifacts created by students, such as the data flows and completed worksheets, and analyzed them then on typical errors. In the fourth phase, we actually reflected on how it went. So at the end of the cycle, we reflected retrospectively about the challenges and decided how we want to adopt the data case study for the next cycle of our design-based research project. So we went through this cycle 3 times, and teachers taught a total of 3 different groups of students. In the first cycle, we had 15 students, in the second 13, and in the third 16 students. And every cycle lasted approximately 48 hours. The result of the research process is actually twofold. So on the one hand, we have a bunch of data cases there, I think 35 data cases, if I'm not wrong, in German language, unfortunately. So some of them are translated into English, but many of them are still in German. So this is a practical teaching material that the teachers can use. And the second contribution is basically the theoretical one. So we adapted the teaching method, the academic teaching method, to the school education, and we developed it further in 3 different variants, as I will show you in a moment. So the school-specific data case study at the end of the research process, it enables students to use, this real-world data with the real world questions to go through the whole data-driven life cycle independently and discover the insights from each step of this data-driven life cycle. So to go through the data practices, reflect on the data practices and concepts, discover it individually. The data cases, they also enable students to develop database problem solving and judgment skills. So there is one type of the data case study that is particularly appropriate for doing so that we can really enable students to create data-driven systems on their own. So every data case study begins with a presentation of a problematic situation that is relevant for a student and the context and the data, so the data set. And then it can be implemented, it can be implemented in 3 different variants, and we call the variants architectures: the bottom-up, the top-down, and the puzzle-like. Each architecture addresses different challenges. So the bottom-up approach, for instance, is a development from the first cycle, which addresses our initial challenges. And the top-down approach is a development from the second cycle, which addresses the challenges of the bottom-up approach. And the puzzle-like is a development from the third cycle, and it addresses the challenges from the top-down approach. Although these architectures, they were developed sequentially, they don't have to be used sequentially in the classroom. So they are really equally valid. And depending on the learning objective and the class, the teacher can decide which architecture to use to address a data case in the classroom. And in the rest of the presentation, I will introduce you to these 3 types of architectures and give some examples of challenges that we experienced. So to overcome the initial challenges, and maybe you remember, so the initial challenges that we, for instance, you knew was a lack of programming skills, lack of the domain knowledge. We developed this very much bottom-up data case approach. Bottom-up means that the students are closely guided to go through the data practice independently, step by step, and discover the insights from each practice themselves. And what I mean by very guided, here's an example on the left. So for instance, the student asked, so drag the data table widget, and you know these bubbles, they are called widgets. So drag the data table widget onto the workspace and connect the output of the widget data sets to the input of the data table. So, you know, it's very much, you know, guided and, you know, do this, and then explore what do you say, what are you seeing here? So there is not, you know, there is nothing that can go wrong here. So the resulting student artifact is on the one side, you know, the data flow. Here on the right, you can see the ready data flow that was constructed in, you know, individually by every single student. And explored. So the data practices that are also in this data flow are explored by students. And on the left, there is a reflection and, you know, discussion of the findings from the data flow, written report, I would say. All right. So the second architecture that I'm going to talk about is a top-down. Maybe interesting because I forgot to say that this very first architecture on the bottom up, it was about Tasmanian sea snails. So it's like, you know, all our data cases that we tried out with the children, they are all about the environmental topics. So they work with environmental data sets. And so this one was about the sea snails from Tasmanian. All right, so the top-down architecture. So it addresses actually two key challenges that we experienced during the bottom-up architecture. So first of all, as I've already tried to show, we had this very much, you know, the teachers complained the challenge that they saw is that we, you know, overemphasize this operating skill of Orange. But then the most importantly, there was no reflection on the data-driven life cycle, no reflection at all, because it's like, because of the overemphasis on the operating skills. And so the top-down approach tries to address these challenges. And it structures very different. So top-down means that each data case begins with a prepared data flow, and it includes a series of interpretation and reflection tasks on data practices and concepts so that the students, you know, can develop the data-based judgment skills. And so typically in the first step, you will ask the students to go through the leaf widgets, so through these widgets, and here's, for instance, you can see the task number 3. So examine the scatter plots, summarize your impression of the trend and any notable features. So they go through this leaf widgets first, and then in the second step, they try to deduce the significance of the widgets in the branch for the final result. So they reflect on the practices that led to the final result of the data flow. And the result is, well, for the first, it's an investigation of the leaf widgets, also in a written report that the teacher can correct and work with and see whether the students get the insights from the domain perspective. But it is also a description, like here on the right-hand side, description of the stages in the data-driven life cycle in a reflective manner that is produced by the school students. All right, so I'll introduce my favorite approach, the puzzle-like. Well, what kind of challenges did we experience with the top-down? Because the puzzle-like approach addresses the challenges. Well, I think the key challenge that we experienced with both the top down and the bottom up was that the case study, it offers very few opportunities for exchange, where the students really need to say something to someone else, where they really get into this real conversation. And we also discovered that it was very difficult for students to debug the data flow, so to understand where the error is happening. And so we developed the puzzle-like data case. So the puzzle-like data case is very different. So it's unplugged. It's without a computer. So we took the Orange 3 to be, we created the Orange 3 unplugged approach. And here the student begin with a set of pieces consisting of widgets, data overviews, templates for configuring widgets. And the task is that they have to reconstruct the underlying data flow and determine widget configurations. And, because they suddenly have to talk with each other, they have to verbalize the concepts. They have also to connect, to think about the data concepts in a meaningful way. And in this process, they discover elements that are essential for debugging the data flow. And this is very important if the debugging, being able to debug the data flow is very important if they want to create the data flow on their own. So the learning product is something like a data flow on a poster, as you can see here. And this is also something that a teacher can quickly assess in the classroom. Now, after testing these 3 different approaches with students and systematically analyzing the challenges through the interviews and the analysis of artifacts, we identified these 3 different architectures. And I think that, they allow students to go through this data-driven life cycle, experience data practices in a data-driven project on their own, very much independently, discover the insights from the data flow on their own. I think the key takeaway is that although these 3 architectures, they were developed sequentially, they are equally valid. So no single architecture can overcome the challenges at once. So depending on the learning objective and the class, teachers can decide which architecture to use in the data case, for the data case in the classroom. Because, some challenges such as lack of programming skills, they are addressed by all of them, but others, such as a reflection of the process, are better served by one of the 3 architectures. Okay, with this in mind, I think that, through this comprehensive work, we created a lot of teaching material and also created a new method for computer science education. The materials that we have, we are publishing on the website, so you can see what we have now on Computing Education DE. And the paper will appear in 2 weeks, I guess, on the ACM Digital Library. All right, so I think I'll summarize what I talked today. So I started by discussing how AI topics are entering formal school education. So if we want our students to learn about rapidly developing data-driven systems in a way that ensures that their knowledge remains really relevant after they finish the school, we really need to organize our teaching around fundamental concepts and practices. And we found that the fundamental role of data was underestimated in the previous frameworks. And so to elaborate on what is important to know about the data, we conducted an extensive analysis of the field and deduced our findings into 133 key data-related concepts and 28 key data-related practices. So you can use a collection of them, both collections, to define the common language for teaching, but you can also use them to specify the competencies. And in the second part of my talk, I spoke about the data case study method that we developed iteratively in the design-based research project to teach data concepts and practices in real school settings. And I would say, although this process was very challenging and time-consuming, along the way we discovered new ways of teaching the data, and I think this is a promising process, like taking teaching approaches from sciences or maybe from academia and trying to adopt them to the school. We very much hope that these 3 architectures, top-down, bottom-up, and puzzle-like, they will serve the computer science teachers and the curriculum developers as means to think about how to teach about the data in computer science lessons. All right, so thank you very much for being with me here in this very content-heavy talk. And I'll now open the room for the discussion.
Can we all just say a great big round of applause to Victoria? And I think now you can kind of see this is why I'm so excited about this work, because we've got the kind of really strong research work that's gone into kind of creating the concepts and practices. And then Victoria's actually been out into the wild, tried it over and over and over again to kind of create these wonderful data cases. Coming up, we've got Carl Emil Bilstrup from Copenhagen University, who's going to talk about the microbit and how you can learn machine learning practices with the microbit, which is very exciting. So all of you have a lovely rest of the day, because we're all at different time zones from all over the world. Lovely to see everybody, and you can turn your mics off and say goodbye now.